Have you ever wondered how scientists predict population dynamics, such as the relationship between predators and prey in nature, or how meteorologists model changing weather patterns? Well, today we are diving into the fascinating world of hybrid dynamic Bayesian networks, or hybrid DBNs. These powerful statistical tools allow us to model complex dynamic systems that involve both discrete and continuous states. Sounds intriguing? Let us get started on how to create a hybrid DBN using GeNIe and explore the exciting differences between hybrid DBNs, discrete dynamic Bayesian networks, and hybrid Bayesian networks. A DBN is an advanced probabilistic graphical model that employs the principles of Bayesian networks while incorporating time as a critical factor. Unlike traditional Bayesian networks that represent a snapshot in time, these models evolve and illustrate how systems change over time. Hybrid DBNs uniquely combine both discrete variables, like those having states high, medium, or low, and continuous variables, such as temperature. This versatility allows for complex and realistic modeling of dynamic systems. Before we jump into creating a model, let us clarify some key components. Nodes represent variables. In a hybrid DBN, you can have both discrete nodes and continuous nodes, like temperature. Directed edges indicate the relationships or influences between nodes. Time slices allow us to observe how these variables change across different moments. Understanding how these elements come together is critical for modeling real-world dynamics. Now, let us compare the four types of networks we mentioned earlier. Discrete Bayesian networks. These only have discrete nodes, making them limited when representing continuous variables, such as temperature, pressure, population size, etc. Hybrid Bayesian networks. These comprise both discrete and continuous variables, but do not represent time explicitly. They capture relationships and dependencies among variables but lack the temporal component. Discrete Dynamic Bayesian networks. These allow for modeling a system development over time, but only consist of discrete nodes. Hybrid Dynamic Bayesian networks. As the most sophisticated of the four, these models can represent both time-dependent changes and mixed variable types, providing a robust framework for representing real-world complexities. Mathematically, this framework allows us for representing systems of difference equations. Next, let us introduce GeNIe, a user-friendly software tool for constructing Bayesian networks. It provides intuitive features for building, visualizing, and simulating dynamic Bayesian networks. Whether you are a novice or an expert, GeNIe empowers you to create hybrid DBNs with ease, thanks to its straightforward interface and powerful algorithms. Now let us build a hybrid DBN using the Lotka-Volterra equations, which model predator-prey dynamics. In our case, we will represent rabbits as prey and foxes as predators. Create two nodes, R for rabbit population density and F for fox population density. Both nodes should be placed on the temporal plate. Next, we should add the parameters alpha, beta, gamma, and delta. Sigma is a parameter of noise that is natural in all real systems. Defining a dynamic node requires at least two equations, one for the initial conditions and another for the temporal relationships. Please note that GeNIe will automatically add arcs based on the equations you enter. Let us define our initial rabbit and fox population densities to be between 5 and 15, which can be implemented in GeNIe using uniform distributions. We will represent the relationships between the population densities of rabbits and foxes by means of the Lotka-Volterra equations, which express the population densities in the next time step as a function of the densities at the current step. Parameters alpha, beta, gamma, and delta represent growth and interaction rates. The max function ensures that the population densities remain positive. Sigma is a parameter of noise that is natural in all real systems and that we introduced in the equations. After creating a hybrid DBN structure and defining key temporal nodes, we can set alpha and beta parameters for rabbits and gamma and delta for foxes. For simplicity, let us assume first that there is no noise in the system. The graph generated for 10 time steps does not show the relationship between rabbits and foxes well, while increasing the number of time steps to 300 clearly shows the relationship. Plate node bar charts allow us to visualize the expected value and standard deviation over time. We can also use a phase space diagram. A phase space diagram is a graphical representation that plots the values of one variable against another variable, illustrating the dynamics of the system. In a typical phase space diagram, the trajectory of the system is mapped, showing the states or values as they change over time. For example, a phase space diagram might depict the number of foxes in a natural ecosystem as a function of the number of rabbits. This type of diagram allows for a visual representation of the development of the system and can indicate the direction of change as time progresses. A fully functional and described model is available in our model repository, repo.bayesfusion.com. We encourage you to check out the capabilities of hybrid DBNs, both with this and other models. So why should we use hybrid DBNs? They allow for more realistic modeling of complex systems, the ability to predict future changes over time, integrating various types of data for comprehensive analysis, flexibility in representing uncertainty, and incorporating observations at different time steps. And with GeNIe, the process of building and understanding these models becomes much more efficient. Whether you are conducting research, studying biological systems, or working in finance, hybrid DBNs can dramatically enhance your analytical capabilities. Do not forget to try GeNIe for your own projects. It is a fantastic tool that opens the doors to dynamic modeling. If you enjoyed this video, please give us a thumbs up and subscribe for more deep dives into the world of data science and modeling. See you next time.